All right, I'm going to attempt to use PowerPoint here. So let me go to my first slide. I think Stan Winston is the perfect person to be kicking off this session because I know I'm not the only one on this panel who's here to stand before you and tell you about the wacky robots that I build, largely because as a child I went to the movies and I saw these science fiction robots and I fell in love with them. And I knew that's what I wanted to do. That's what I wanted to make real. So today I'm going to tell you about my wacky robots. I think it's interesting when we look at science fiction. Of course, they've always presented very vivid images of what robots might be sometime in the future. And I think it's interesting that our attitudes about what robots might become has continued to evolve, at least in American science fiction. You know, way back in the early days, we had this sort of, robot as a worker drone. But as time's gone on, such as like in Star Wars, robots started to take on many more human characteristics. They started to take on very rich, complex personalities, complex emotions. They became our friends. They stood by us in our time of need. They shared our daily lives in very rich ways. And I think one of the qualities that really captured our hearts about these science fiction robots was the fact that they were socially intelligent and they were emotionally intelligent in a human-like way. And that's a lot about the theme that I'll be talking about today. So the vision, as George was talking about, of robots playing a part in our daily lives, it's going to happen. In fact, some people may argue it already has happened. The ways we're going to be interacting with them, the relationship we're going to have to them is going to take a number of different forms. For instance, here I have 4 different categories of human-robot interactions and the kinds of applications you're already starting to see in these domains. The most traditional one perhaps being robot as a tool that we see as an extension of our bodies that allow us to perform and do things that we couldn't do before. So whether it's something like a remote surgery robot that improves the precisions of a surgeon's movement, or a planetary rover that allows a scientist to conduct experiments on a far-off planet, this idea of robot extending our abilities such as a tool. Robots are becoming even more intimately coupled to our bodies as well. So whether it's a robotic prosthetic that's helping to replace lost functionality, or new movements, exoskeletons and so forth that give us superhuman abilities to extend and augment our capabilities are coming to the fore. And technologies such as brain-machine interfaces are very hot fields right now. Another area that I think I would put Stan's work in the category of is robot as a communication medium. And a lot of what you can think of Stan's work as being is essentially robot-mediated performance. Now, what if it wasn't just a technology that a puppeteer could use to communicate people, but an ordinary person? It could be a very rich, embodied way of communicating with people across the world. And we're starting to see, this is a prototype, or I think it was a product actually, Helen Greiner, iRobot. So we're starting to see the very first remote presence robots becoming commercially available to us. So I think this is going to be another important trend. And the one that I'm going to talk about and focus on today is this idea of robot as a social and cooperative partner. And this is really kind of the science fiction vision that I alluded to in the previous slides. So whether robots are going to be teammates, such as the work that Rob Ambrose is doing, caregivers to the elderly. This is a very important application motivating humanoid robotics in Japan. Entertainment, of course, Sony. You'll actually be seeing a fabulous demo here about robots as an entertainment technology, or in education as tutors or museum docents or whatever. We're starting to see robots take all these different forms. So if we're going to talk about building robots that can be an effective cooperating partner with people, what is that? What does a robot really have to do to make this happen? And to wrap our heads around this, we can think about an example here where you have 2 people performing a cooperative physical task together. You've got a guy with a drill here who's trying to drill a hole, and you've got this other guy who's kind of helping him out. Now let's say you have the situation where this guy here is trying to drill a hole for a mounting plate. So he orients the plate, he gets his drill set up, he starts to try to drill, but the piece slips. And so he stops, he starts it again, orients it, the piece slips again. So if this guy's going to be a cooperative assistant, it's going to be really important for him to be able to understand the goal and the intent behind these series of actions. So this idea of understanding the person's intent behind what they're trying to do. If he could do that, then obviously what he would logically do is reach out, orient the piece to allow his friend to drill the hole. But he's also going to have to be able to do perspective taking, so that he can't orient the piece that would be convenient for him to drill the hole, but hold it in a place where his friend could drill the hole. So this idea of being able to take the perspective of another is also critical. He may notice that the place where the person was going to drill the hole is rotted, and he was going to want to direct his friend's attention to that place. Say, look, this is a problem. Have a dialogue about that. All of these skills are going to be really critical to a robot that can actually be a cooperative assistant to a person. And it turns out that all of these capabilities and more are part of a greater human competence, which in the psychology field is called theory of mind, or theory of understanding other minds. And basically, this is our ability to be able to infer mental states, the intents, beliefs, desires, emotions of other people, and that cause action. It's our natural way of understanding why people do what they do, and it's what allows us to understand and predict people's behavior so that we can formulate appropriate anticipatory responses. And it is this ability that really underlies our ability to cooperate, communicate, and learn from each other in our human-like way. Now, this is an ability that's so fundamental to our social intelligence, to what we are as humans, that we take it for granted. But it's actually a very sophisticated competence. In normal human children, it takes about the first 5 or 6 years of life to develop. That's long after language. And a deficit of theory of mind can be devastating, as is the case of autism. This is critical to what makes us human. So just to give you a sense of this mind-reading ability, this ability to infer mental states from situational context and behavioral cues, we're going to run through a couple quick examples. So here's a standard test question that an experimenter might give to a child to infer their ability to decide or for mental states of a person, such as desire, from gaze direction. So they show a child this picture here, and they'll simply ask them, what does Charlie want? Which candy does Charlie want? And of course, for us, the obvious answer is the candy that Charlie's looking at. And of course, that's what normal 4-year-olds will answer. It turns out that autistic children will answer at random. And normal 3-year-olds will either answer with their own favorite candy or will behave at random. You think they could answer this right, but it's fairly tricky. Here's a cross-species example. This is to assess whether an animal, or even in this case a child also, understands the concept of seeing leads to knowing. So you have these two experimenters. One of them has their vision occluded by having a bucket over their head. This other person has non-occluded vision. A third experimenter comes into the room, hides a piece of food that this chimpanzee wants within this box in one of 4 cubby holes, and leaves the room. Now, the chimpanzee can choose whose advice to follow based on seeing this. And of course, again, what you see is that normal 4-year-old children get this right. Turns out chimpanzees perform at chance, although over time they can learn the cues that are relevant to solving this task, and normal 3-year-old children can't do this. So again, this seems obvious to us, but it's not. So what does this mean in terms of building robots or building cooperative robot partners? Well, not surprising in the field today, robots are rather heavy on understanding objects and physical interactions, and relatively light. I mean, there's not a lot of effort, but there's a growing effort in trying to understand people and social interactions. I think clearly we're going to need to remedy this balance, which a lot of my work is directed towards, if we're going to build robots that really can cooperate with people as effective assistants and learn from them. And one of the very pragmatic applications of this is what Rob Ambrose will tell you later today about Robonaut, which is a humanoid robot that's envisioned to be an astronaut's assistant. So there's immediate applications for this technology. We're actually in collaboration with NASA right now, along with other universities, to do just that, to make this ability autonomous within robots. And of course, this is really critical if we're going to effectively introduce these robots to play a part in our daily lives with ordinary people. Okay, so that's my position statement. For the remainder of the talk, I'm going to be going rapid fire through a lot of examples of social skills that we've been building into this robot so you can get a sense of where the field stands today. I'm going to be giving examples for 2 robotic systems. The first is Kismet, which some of you may be familiar with. It's the one George mentioned in the introduction. It's an older project and the predecessor of Leonardo, which of course Stan Winston introduced. Leonardo is a fairly new project. It's been going on for about 1.5 years. So a lot of this work is in its early stages, getting kind of the basic sensory motor skills down, but you'll see where the work is going so far. So I'm going to go through these abilities very quickly. The first is the ability to establish shared attention. In that example I gave earlier, the ability to direct someone's attention is a very important skill, to be able to share the same perceptual experience about the same thing at the same time so you can have a conversation about it. The second one is expressive readable behavior, so that the robot can communicate its internal state to a person. Now, this is important because people are going to use their own theory of mind in order to try to understand the robot. So the robot has to display the same cues that are those hooks that allow the person to do that. And in fact, you could argue that this is just good design principle. The design should be transparent. The robot has to reveal itself to you through its behavior. The third one is the ability to share affective state with humans. And George talked about how important he sees emotions as being in the future work of robotics. Then more conversational skills such as turn-taking. And then finally, I'll end with facial imitation. So it's important when you want to direct the attention of a robot that the robot be able to respond to the same natural cues that people use to direct each other's attention, as well as provide the behavior cues so that the person knows when they've succeeded. To implement this, we adapted a model proposed by Jeremy Wolf, who's a very well-known psychophysicist at Boston University, who studied human visual attention and visually guided search, and came up with the following model here, where he argues that attention is basically the result of both bottom-up influences coming from the environment, things with innate raw saliency, such as bright colors, motion, in the case of Kismet, skin tone, that are combined through a weighted average to produce the saliency map, and of course the robot's gaze should be directed to that region in the image. But it's also influenced by top-down task-based information, which basically can change the relative weighting of these gains so that the robot can show a looking preference, say, to brightly colored objects if it's trying to find a toy. And when this unfolds, oops, how do I go back? Now I'm in trouble. Right button. When this unfolds during a natural interaction, you'll get a sense of the flow where the robot is always looking at the appropriate thing at the appropriate time. Do we have sound actually on this? Here we go. So Kismet is not speaking English. He's just taking a speaking time. So he's looking at his face. When he gives this attention cue, it looks at the watch at the right time. And it's a very natural interaction.
I almost lost it this week.
And even as he shifts and as he gestures, the robot follows that as well. So again, what the robot looks at is appropriate at the right time. And this is very fundamental, as Stan mentioned, to just fundamental social behavior. Okay, so that's shared attention. Now, the other thing that Stan mentioned at the end, which was an interesting technology, is if you could do this, well, could you give animatronic robots this ability to track objects and so forth, so that a puppeteer now could play the role of the attentional system, essentially take a tablet PC interface, say, choose what you want the robot to track and have it do it that automatically. So here's a video showing me doing a color clustering algorithm here to pick a target. It works on skin tone as well as basically any color pattern. This is the tablet PC interface. We have the eyes here. This is actually an early armature that Stan Winston Studio gave us for the eyes that eventually went in Leonardo, but you can choose what target we want the robot to look at, and it's able to smoothly pursue that target. So again, this is an early armature. During the month of August, we'll be porting this to Leonardo for the full-bodied articulation. All right. Another skill is the ability to express its affective state. There's a very rich literature, as you might imagine, that relates the psychology of facial expression to the underlying emotion. And the model that we adopted is called a componential approach, or a componential theory, where the argument is that emotional categories such as fear, anger, and so forth are mapped onto a set of lower-level affective dimensions, and that the features of the face move in correlation to where you are along these dimensions. So they actually convey information along this lower dimensional space. So for instance, as you go up on the arousal axis, a person's eyes might widen, their mouth might open, they might become more erect, their eyebrows might raise. As you move down, it's the opposite. They become more relaxed, the eyes droop, and so forth. So we did this approach where Kismet's emotion system is essentially responsible for taking all this stimuli coming into the robot and appraising it along these affective dimensions, and then mapping these dimensions onto the robot's face. So literally its face becomes a window as to how it's appraising the world. So here I'm just going to show you a quick video of Kismet expressing in 3 modalities, in facial expression and posture, and even in tone of voice. We need more sound? So it's saying the same thing. Do we really think so?
Do you really think so?
It's anger.
Do you really think so?
It's disgust.
Do you really think so?
Fear.
Do you really think so?
Happiness.
Do you really think so?
Sorrow.
Do you really think so?
And interest. So that's expression. Now, Kismet, of course, was just this head-neck system. Of course, the ante is upped, obviously, when we're talking about something like Leonardo, which has 66 points of motion, full skin that gives it a very organic appearance. Here you're seeing some of the expressive ranges of motion of Leonardo. It's actually being teleoperated right here. Here you're getting a sense of the subtlety and the richness that you can get out of the face. So some of the techniques that we've been exploring, we're in a collaboration with the Synthetic Characters group at MIT. I'm sure many of you know the work of Bruce Blumberg, looking at some of the techniques that actually this community has been exploring, the motion, animation, blending verbs and adverbs and so forth, to look at how do you coordinate these multiple degrees of freedom. So here's a little eyeball you control with a mouse, and this is, of course, in our virtual Leonardo simulation. But here he's coordinating multiple degrees of freedom, the torso, the eyes, and so forth, in order to display the motion. So this is going to probably be one of the key tools that we use to actually generate the motion trajectories for full-bodied Leonardo. Next slide. So we've talked about expression, and what about recognition of effect as well? For this work, we were inspired by the work of Anne Fernald, who's a developmental psycholinguist at Stanford University. And she's discovered that there are 4 prosodic contours, or melodies of voice, that infants seem to respond to as early as 6 months of age, so long before they're speaking their first words, for effective content. And these are contours for approval, prohibition, attention, and comfort. So I'm not going to go, obviously, into any technical detail into this, but even if you look at something like energy variance versus pitch mean in the feature space and a bunch of utterances, you see some nice partitions in this space according to arousal, so soothing versus higher arousal states such as prohibition and attention, and even in valence. So lower pitches have to do more prohibition and higher pitches have to do with attention and approval. So we developed a multistage classifier. It's a mixture of Gaussian model with EM, where for the more difficult to partition cases, we used more of the features that Anne Fernald suggested as being critical for how infants do this. And we hooked this up to Kismet's emotional system and had naive subjects come and issue these intents to the robot. And we saw some pretty interesting interactions. It doesn't matter what language you say because it's tone of voice. 5 minutes? Okay.
Bien sûr. Nice robot. You're such a cute little robot. You're so serious. Good job, Kismet. Very good, Kismet. Look at my smile. Oh, that was cute.
Okay, these are attentional bits to get its attention.
Kismet? Hey, Kismet. Ah, there we go.
Vite, vite. Regardez. Ici.
Kismet, do you like the toys? Oh.
Okay, these are scoldings.
No. No. You're not to do that. No. Not appropriate. No. No.
So it goes down even further. Now, this was the first time she scolded the robot, and it goes into a full frown, and she's always looking a little distressed that she's upset this robot.
Where'd you put your body?
So after you scold it, you have to soothe it.
Très bien.
Oh, you're better than I was.
Okay, you didn't hear that. Okay. So that's recognizing effect and responding to it. So what about, this is all about effective interaction so far, but what about some more conversational sort of interactions? So again, Kismet doesn't speak English, but it's more like modeling pre-linguistic infants. So you can have these proto-dialogues with it where you don't understand what it's saying, but it doesn't matter. It's really about the timing and the rhythm and the dynamics that make you feel like you're in communication with this robot. And it turns out that's really critical. So it turns out, of course, that people, when we communicate, it's not just through language and speech. We communicate with our entire body. And our bodies serve multiple functions. And one of the critical functions that our gestures and our facial expressions and so forth serve when we speak is to help regulate the exchange of speaking turns. And these are called envelope displays. So things such as when I'm done taking my speaking turn, I'll often make eye contact with the person and raise my brows to signal that I'm done speaking and I want the person to take the floor. If the person takes the floor, they might break eye contact, they might lift their hands as if to start a gesture or something, take their speaking turns, and then go back. So we implemented these envelope displays on Kismet to see if people would use them to help regulate the exchange of turns with Kismet, and if that would make the interaction smoother over time, and we found that it actually did. So here's some video of that. I apologize, there's going to be a pretty strong background noise in this, but you'll get a sense of these cues. So it takes a speaking turn. And it poses you for the next, to take your turn by raising its mouth and making eye contact with you.
And how was that?
Here it's breaking eye contact. Its attentional system actually is having the robot look at this other person, which is nice because it has this effect of including two people in the conversation. And if it even takes multiple utterances, I know not to speak because it's not making eye contact. It hasn't handed me the floor yet. So it turns out that these cues work even for robots, and it's very easy for people to pick up on these cues. Okay, so I know I'm running out of time. So I'm going to wrap up with, I've been talking a lot about social skills, and I want to get back to this bigger question of how do you get to theory of mind. And it's a tough question. It turns out that in the psychology literature, imitation, early imitative abilities and imitative exchanges between caregivers and infants is believed to play a very important role in development of theory of mind in normal human children. You can imagine that these first imitative exchanges are primordial like-me experiences. This appreciation there are other things out there in the environment that are like yourself, where the child from these experiences can discover these sort of self-other similarities. These exchanges are fundamentally bidirectional. It turns out when the infant is very, very young, it's far more often the mother who imitates the infant than vice versa. And they're very contingent. So over time, the infant learns how it can modify its own behavior in order to shape the behavior of the adult. And it turns out that this plays an important role in bootstrapping this sort of turn-taking competence. And of course, over time, the imitative ability develops in its own right to become a very powerful social learning mechanism for things such as skill transfer, which actually has already been explored in the robotics community. Now, Andrew Meltzoff is a very well-known psychologist who's been looking at imitation and its relation to theory of mind for many, many years. And he argues that it's a very powerful procedure for understanding persons, and that basically to have the child learn how to take the role of the perspective of another is critical, and that this shift in perspective might allow the child to essentially use its own cognitive machinery that it would use to generate action as a sort of simulator of the other running in reverse to figure out, well, what might I be thinking, what I might be feeling, what might my motivations be, my goal be, in order to cause that action. So it might be a way of actually inferring intent in this very kind of embodied way. So this is an approach that we're starting to try to explore on Leonardo. And we've looked at facial imitation. This is apparently a very well-studied area, partly because it happens for human infants within hours after birth, which is a strong argument that this is an innate ability. It's also interesting because it's cross-modal. So while the infant can see the parent's facial expression through the vision modality, it has to experience it in a different modality, which is this proprioceptive ability. So how is it able to do this mapping? The argument is the child, through these early interactions, is learning this sort of intermodal map, which is shown here. And they have the ability to sort of have a rough mapping of features. So they kind of know that mouths go to mouths and so forth, but they don't know the specifics of how the mouth moves and such. And they have a motor babbling phase, so they're able to experiment in their motor space and have sort of goal-directed process. So we implemented this model on Leonardo to explore this ability as a first step towards looking at imitation as a route for theory of mind. And should I run out of time? Okay, let me wrap up. So you saw that. Okay, at least the picture of it. So again, to wrap up, I started this talk trying to argue in this bigger picture of that theory of mind is really, I think, one of the grand challenges in building robots that can really be effective for cooperating and learning from people. Of course, giving a lot of highlights as far as building social skills in the robot, and of course, the importance of imitation in this process as the next steps. And I've also tried to touch on a few applications for potential impact, both in the entertainment field as well as human-robot cooperation, such as my collaboration with NASA JSC. So I'm going to end here.
Good.
Thank you.
Thank you.